Hey all, welcome to today's class, and today's class will be about simple linear regression. And by simple linear regression, it's essentially one dependent variable and one independent variable. Econometricians often call it as one explanatory variable and the other one is an explained variable. I'll get more into this soon. Now we talk about what is simple linear regression model. As I briefly mentioned, it is the regression between one dependent and one independent variable. If you're confused by the term independent and dependent variable, think about it as home prices. Home prices can be a dependent variable for some equations and an independent variable for other equations. For example, we are talking about how much property taxes are collected in a given country. At that point, we'll consider home prices to be an independent variable since that defines the home property taxes. Flip the script. Let's say we're talking about the home prices being defined by number of bedrooms. So the number of bedrooms would be independent variable and the home price would be dependent variable. Now you can argue back and forth for all of these things, but at the end of the day, this is the very crux of how we use an independent and how we use a dependent variable. As I was talking about it, I did inference some level of causality. However, it is very important to note that causality cannot be defined in this particular case until and unless the data that's collected is randomly collected. So in the last lesson, we talked about random data collection. Over here, think about it as, let's say I have a big classroom and I ask random 20 students to give me their household income. I can make an inference about something. Even then it'll be something more sort of a biased data collection because I'm looking at a classroom. But let's say if I go out on the streets and I take a random collection from a very general public street, I might get a more greater interpretation of that particular region or locality. And that's when I can inference causality. However, in most cases, causality cannot be defined until and unless data is purely randomly collected. That said, moving on to what a simple linear regression could look like. Simply speaking, it's defined as yi is equal to beta naught plus beta 1 plus x times xi plus ui. Each of these terms have a separate meaning and each of these terms are very important. Yi, as I just mentioned, is the dependent variable. Remember, y dependent. It's a dependent variable on the ith term. You've got a huge database. You've got an indexation. Assume that every data point has an indexation. The ith term is the indexation attached. The 1, 2, 3, 4, 5 for every dependent term. Beta naught is the slope intercept. Think about it as concepts from your high school where you learned about y is equal to mx plus c, which is used to define a simple straight line on a curve. So you define the slope of the curve and you'd usually use these for demand and supply functions. Similarly, beta naught is the c, the constant term on every equation that we talk about. Beta 1 is the slope coefficient. It's the angle of the slope. So remember that beta, when we used to write y is equal to mx plus c in school, that m is the slope coefficient. M is written as beta 1. We write it as beta 1 because there are going to be a lot of slope coefficients that are going to come in play. And so it's important to start off here. Perfect. Now we talk about the core property that helps us get to the final stage. The final stage, just for spoilers, and it's mentioned on the slide, it's to create an OLS regression. I'll talk about OLS regression soon. But the core property that's associated is that when you have the UI, not talk about this. UI is the error term at the ith indexation. When you have the UI, which is the error term, along the entire x-axis, you could assume that it just zeroes down, as in X does not have an effect on the value of U. In other words, when if we have a situation where as X increases, the error term UI increases, then a conditional mean independence property is violated. So there should be no relationship between the, the independent term and the error term UI. I could imagine that must be a little confusing. So here's a greater explanation about exactly what that conditional mean independence means. In very simple terms, it's when the independent variable does not impact the dependent variable. But hold on, Sarthak, you just said that we're talking about the error term. Yes, when you think about the entire equation by itself, the equation is defined as y is equal to beta naught plus beta 1x plus ui. So the if the independent variable impacts the dependent variable, which means that there's a correlation between the error terms. And that's why we note it as expected value of xi given ui is 0, or expected value of yi given xi is equal to beta naught plus beta 1x. In other words, when you look at a large number of x's, the errors can be on either side of the slope. And this slope, what we're talking about, will be developed through the OLS. So it can be on either side of the slope. And eventually, the either sidedness of errors will eventually cancel out, which will give us that the expected value of xi or expected value of ui given the latter is equal to 0. Perfect. Now we're on to the OLS. What is OLS? The concept of OLS is very simple. It is that we want a line, the y is equal to mx plus c, that we learned in high school, but here we're talking about beta naught and beta 1. We want such a line that best fits our data. So what do we say? When do we say that something fits really well? When you talk about your clothes, you say that the clothes fit really well because the shoulders do not sag a lot, or it's perfect on the neck, or it's perfect on the belly. Similarly, you've removed the error term from either sides and you've got a function that best fits the data. And so what you do is that you minimize the sum of errors, and that's how you get ordinal least squares. Least is the core function of it. I'll show you a brief calculation of about how to go about it and regarding exactly how it is calculated. So what do we mean by the process of calculating ordinal least squares? There are three core steps involved. Step number one is arranging the equation. Now, what do we mean by the equation? I'll briefly talk about it. Then step number two is calculating the ordinal least squares, which is we minimize the sum of squared error terms. And this way we get the best efficient line. And then step three is the calculation of the OLS estimates. The estimation calculation is pretty easy, but here I go through the entire process of how do we get those funky numbers. Now, bouncing in on step one. Step one is we arrange the equation. How do we define the equation? So our equation is equal to y equal to beta naught plus beta 1 xi plus ui. Our goal is to minimize the sum of ui squared. So what do? We take this particular function and bring it forward. So we have ui is equal to yi minus beta naught minus beta 1 xi. Calculating step 2, where we minimize the sum of error squares, which is equal to minimize sum of yi minus beta naught minus beta 1 xi squared. Now, where do we get from here? Because now this is a very strange place to be. So what we do is we calculate first order conditions with respect to beta naught. This is the first step 2.1, I'd say. All right. So when you take a derivative of this with respect to beta naught, you have function divided by beta naught, and you have 2 summation of yi minus beta naught minus beta 1 xi times minus 1, because you're taking the derivative with respect to beta 1. We know that first order conditions are always equal to 0, and hence dividing both sides of the equation by -2, we have summation of yi minus beta 0 minus beta 1 xi is equal to 0. Now one thing that I forgot over here, as soon as you take the first order condition, you get the predicted values, because you're already taking it with respect to the slope. So now, since you've calculated this already, we'll move on to the next step, that is opening up the brackets a little. So we have summation yi, we leave the beta naught as it is because it cannot be summed up, and eventually we can sum it up. Let's say we sum it up, and then you have the summation of beta 1 hat and summation of xi hat xi, which is equal to 0. Let's say we divide both sides of the equation by 1 over n. So divide by 1 over n, and hence you have y bar minus, now since beta naught hat is constant all throughout the term, we get beta naught hat back. Since beta 1 hat is constant all throughout the term, all throughout the process, we get beta 1 hat back, and we have mean because we're taking the sum of something, dividing it by number of observations, and we get mean, which is equal to 0. So now, just going back a couple of steps, let's mark this as equation number 1, and then we have our core equation number 2. Solving this further, you have beta naught hat is equal to y mean minus beta 1 hat x bar. Let's call it equation number 3. Let's go back to equation number 1. There are more steps left, but this is where it gets interesting. Now, recalling our equation number 1, through our step 2.2, we have derivative of the function with respect to beta 1, which is equal to derivative beta 1, and here we have summation of yi minus beta naught minus beta 1 xi whole square. Close the brackets. Taking a first order condition, you get y 2 times summation of yi minus beta naught. Again, remember, what did we do the last time? We added the predicted values right away. Beta 1 predicted xi times, since we're taking a derivative with respect to beta 1, we also have the xi as the remaining term, which is equal to 0 because first order condition. And we also have the negative sign which we have, so let's add it over here. Now, using the same process of dividing it by -2, we are left with summation of yi, I'm just going to write a curly bracket over here, minus beta naught hat minus beta 1 hat xi times xi is equal to 0. Now this is where it gets interesting. Let's recall equation number 3. What do we have? So from equation 3, we know beta naught hat is equal to y mean minus beta 1 hat x mean, which implies summation of yi minus y bar minus beta 1 hat x bar minus beta 1 hat xi times xi is equal to 0. Summation of yi minus y bar plus beta 1 hat x bar minus beta 1 hat xi this, and then you have xi close curly equal to 0. Let's open up the brackets now. By opening up the brackets, we get summation of xi yi minus y bar plus summation of beta 1 hat xi x bar minus xi is equal to 0. What do we get? From all that we've observed above, when we take the equations in the right order and we send this across to the right hand side, we have summation of xi yi minus y bar is equal to the summation of beta 1 bar hat xi times xi minus x bar. Now remember that I've interchanged the positions over here because I've taken it to the right hand side, is equal to this. What can we cancel out over here? We right away see that we can essentially get beta 1 hat out and have this equal to summation of xi yi minus y bar divided by summation of xi minus x bar. Now, one core thing with summation problems is that you cannot really cancel these terms because we're taking the sum of the entire thing together. And if you try to recall your earlier class lessons, like from your earlier statistics days, you'll realize that when you distribute this, you get something that's equal to summation of xi minus x bar times yi minus y bar divided by summation of xi minus x bar whole square. I don't make the rules, these are statistics rules. So just try to recap these things, and hence it'll really help you a lot in understanding econometrics. But put a little more pressure. I know it's been a long time since you did statistics, but so put a little more pressure into understanding what this could really mean. Beta 1 hat perhaps becomes the covariance of x and y divided by the variance of x. However, Sarthak, you'd say that covariance of x and y is actually equal to summation of xi minus x bar times yi minus y bar divided by n minus 1. Yes, I agree. But at the same time, the variance of x is also equal to summation of xi minus x bar whole square divided by n minus 1. So the n minus 1's get cancelled out, and hence you're left with beta 1 hat, which is equal to covariance of x and y divided by variance of x. And this implies recalling our equation number 3. Remember, our equation number 3, we have beta naught hat is equal to y bar minus beta 1 hat x bar, which is equal to y bar minus covariance of x and y divided by variance of x times x bar. And that, my friends, are your OLS estimators. Thank you so much.